In this video, we're going to clarify the difference between something called a quadratic relation versus a quadratic equation. They have an awful lot in common. You'll see that when we compare them side by side, the only difference is that here we have a y and here we have a 0. So this relation applies to a whole lot of points that can be on a parabola. We can take an x value and a y value that's on that parabola, sub it into this equation, and we should find out that left side equals right side. If it doesn't, then we know that the coordinates of that xy point are not on this parabola. But here, because we have y equals 0, what we're looking for very specifically are the values of x when y is 0, which means that they have to be the x-intercepts. Okay, so the values of x here, they'll either be none that work, or 1 that works, or 2 that works. There's a couple of possibilities. We're not going to call the x-intercepts anymore. We're going to give them a new name. We're going to call them the roots of the equation. Okay, so when you are asked now to solve a quadratic equation, solving specifically means finding the roots of that equation or finding the x-intercepts for that particular parabola. So we already have some skills to be able to do this, and that's the focus of this lesson, is just to dust those off a little bit. The primary way by which we can find roots is to convert this standard form equation here into intercept form or factored form, because that will help us get the roots just by inspection. So we're going to begin by doing a little bit of review of factoring. So if we have x squared plus 7x plus 10 equals 0, and we're told to solve, that means we want to convert this into intercept form. So how do we do that? Well, we notice that this is a trinomial with decreasing powers of x by 1 each time, x squared, x to the first, and x to the 0. So to convert it into intercept form, we factor it. We need two numbers that multiply to give a times c, or in this case 1 times 10, and that add to give the b value of 7. Can you think of what they might be? Well, in order to multiply to get 10, we only have a couple of scenarios. And notice that both are positive, so both of our options for factors here will also be positive. We can have 1 times 10, and we can have 2 times 5. Quite clearly, those don't add up to 7, but these ones do. So we can replace this then in factored form with x plus 2 and x plus 5 equals 0. Now, in order for the left side and the right side to be equal to each other, if the right's 0, that means that one of these has to be equal to 0 as well, because 0 times anything would give me 0. But I have two options of where 0 might be because of the multiplication of these two terms. We might have that x plus 2 is equal to 0, or we also might have, we have the possibility of x plus 5 equaling 0, which means that x is equal to -2 and x is equal to -5. And these are what we call the roots of the equation, or where this parabola would cross the x-axis, -2 and -5. Now, when we're asked to check to make sure this works, what we're going to do is sub each of those values back into the equation and see if it works. So we could do this mentally, but I'll draw it out to show my thinking as well. I'm going to put -2 in first. And let's see, in fact, if we do get left side and right side equal to 0. Well, -2 squared is 4, and 7 times -2 is -14, plus 10 is 0. I have 14 positives and 14 negatives, so 0 equals 0. So therefore, I know that this is in fact a root. I can do the same check by putting -5 in. -5 squared plus 7 times -5 plus 10 should equal 0. Let's make sure it does. -5 times itself is 25. 7 times -5 is -35. Add 10, set it equal to 0. Does it equal 0? Well, 25 and 10 is 35. Minus 35 means 0 is 0. And so this is how you can check to make sure that your roots work. They should be able to go back into the equation, and they should come out equaling 0. Let's try another example. Let's do 2x squared minus 7x equals 0. And if we're asked to solve this equation, or in other words, find its roots, we can do so by factoring it. So I'm looking at this and I don't have a trinomial. And I remember from chapter 5 that the first rule of factoring is to see if there is a greatest common factor. I did not do that here, but I hope you recognize that there wasn't, in hindsight, now that we look back. Here, is there a GCF? Yes. They both have a factor of x that can be taken out, which leaves us with 2x minus 7 equaling 0. So again, two things are being multiplied by each other. As long as one of them is 0, the entire left side will be 0 too. So let's see what those two roots would be. Well, the first one is that just simply x itself could be 0. The other option is that 2x minus 7 could be 0. If we rearrange and solve for x, I'm going to take the negative 7 to the other side by adding 7 to both sides. And then I'm going to get x by itself by doing the opposite of multiplying by 2, which is to divide by 2. So x equals 7 halves, or 3½ if you like. We could do a check to make sure this works as well. So to check, I'm simply going to sub each of those values back in one at a time to see if left side and right side are the same. So my first check is to put 0 in wherever there was an x. Now, I'm not going to write this one out because I think by inspection you can see this term will become 0 if I put x in equals 0. So will this one. Left side and right side will both be 0. Let's check the 7 halves one. So let's do 2 times 7 halves, quantity squared, minus 7 times 7 halves equals 0. I have to do exponents first before I do multiplication. So 7 halves times 7 halves is 49 over 4. Minus, I can multiply this out if I like. It comes out to 49 over 2 equals 0. Here, I can recognize that I have a factor of 2 on the top, and 4 is 2 times 2 on the bottom. If I take out a factor of 2 on the top and a factor of 2 on the bottom, I'll get 49 halves. And so 49 halves minus 49 halves is 0 equals 0. So again, this root works out quite nicely. Let's do one more example using factoring to try and find the roots. Let's say that you have 4x squared minus 4x equals 15, and I say to you, solve. Again, solve means try and find the roots. So I don't have an equals 0 here because there's a 15, but I could make it equals 0 if I bring the 15 to the other side with its other term type friends. Now I've got something here in trinomial form that I can try to factor. So is there a greatest common factor? No. I'm left with a trinomial. Is it a perfect square trinomial? Well, 4x squared is a perfect square, but negative 15 is not. So it's already failed one of the 3 PST tests, so I can't factor it as a binomial times itself. So my next step is I'm going to have to use a thinking chart. I'm going to need 2 numbers that multiply to give 4 times negative 15, or negative 60, and they have to add to give negative 4. Can you think of what those 2 numbers would be? Well, if I try 1 and 60, there's no way they're going to add to negative 4. These 2 numbers are going to have to be fairly close to each other. I wonder about maybe even trying 15 and 4. Well, they're not quite close enough either. One of them has to be negative in order for them to add to give a negative value and also multiply. If I did that, I'm going to end up with negative 11. So I need 2 numbers that are even closer to each other. So let's see. If I start working my way down from 15, maybe I could get to, let's say, 10 and 6. There they are. Okay. They add to give negative 4 and they multiply to give negative 60. So here you can either split the middle term or use the Berry method. I'm going to show split the middle term. So I have 4x squared, and instead of negative 4x, I'm going to put negative 10x and positive 6x. It doesn't matter what order they go in, you'll get the same answer either way. What I might do here, just because I can see this, I see that 10 and 15 will pair up really nicely when I'm factoring, when I'm going to start grouping them, and 4 and 6 will be nicely, but we could leave it this way too. Let's take the GCF out of both pairs. So here I have 2x, and I'm left with 2x minus 5. And here the GCF looks like it could be a 3. Okay, I'm going to take out plus 3, and I'm going to be left with 2x minus 5. And we know this happens when we do factoring by grouping. We get a binomial as a GCF, which is 2x minus 5 times 2x plus 3 is 0. Now to find the roots, I know that as long as what's inside this bracket or this bracket is equal to 0, the entire side will be equal to 0. So can I figure out what those values might be? Well, let's set 2x minus 5 equal to 0, and let's do 2x plus 3 equal to 0. Here, I can start solving by x by taking the negative 5 to the other side, mathematically by adding 5 to both sides. So I get 2x equals 5. If I divide both sides by 2, I get x is 5 halves. And no worries, it's okay to have an x-intercept that's not an integer or a counting number. This is just 2.5, no big deal. Let's do the same thing here. Let's get rid of the plus 3 by subtracting 3 from both sides, and then get rid of the multiply by 2 by dividing by 2. X is negative 3 halves. Okay, so it just means that when we have a parabola, it's going to cross at negative 3 halves and 5 halves. Those are its roots. Okay, no big deal. Now we could also solve and check, but I think you get the idea. We have to sub them back in and show that left side equals right side. We could do that here, or we could do it here, because it's the same equation, just rearranged. For the sake of time, I'm going to leave that one there. Okay, let's do another example of solving for roots, but this time let's put it into a problem scenario. Let's go back to throwing some objects, because throwing objects and working with gravity is kind of fun, right? We're going to have a rock being thrown off of a cliff. Okay, I'm going to draw it in this direction. We could go the other way too, but we'll work in the positive sense. We know that here's the cliff face, okay? Here's like the grass, and then there's maybe the cliff where it drops off. It's kind of like Roadrunner and Bugs Bunny idea, okay? Here's a little person throwing that rock, okay? And this is height. It tells us it's measured in meters. And this time we're going to put time on this axis, and time is going to be measured in seconds. All right, and the equation for this is given as h equals negative 5 t squared plus 30t plus 135. All right. So first of all, how tall is the cliff? Okay. How tall is the cliff? It means that we're looking for the value of the y-intercept right here. And what's the easiest way to find that? In standard form. That final term ends up being the height of the cliff, because if time is equal to 0, which it is right at the origin, if we go straight up the y-axis, these two terms will cancel out and we'll be left with 135. Okay, so h is equal to negative 5 times 0 squared plus 30 times 0 plus 135, or the height initially is 135 meters. It's a good cliff. Part B, what is the maximum height of the rock, and when does this occur? As soon as I see the word maximum or minimum, I know that I'm talking about the height and the time it takes for the highest point or the vertex of that parabola. So how can we solve for the vertex? Well, we can take this and we can complete the square. So let's do that. Remember, the first step of completing the square is to bracket the x-axis containing terms. In this case, they're t's instead of x's, no big deal. The next step is to take the value of a out of this as a GCF for both of the terms in the brackets. So I have negative 5 times t squared minus 6t, because I want these two to multiply to give 30, okay, plus 135. Our next step, completing the square, is to make this a perfect square trinomial. So, in doing so, I'm going to take half the b value, which is negative 3, square it, makes it plus 9. But I can't just put plus 9s anywhere randomly in an equation. I'm going to subtract 9 as well so that I don't alter the equality of the equation. The next step is to get the negative 9 out of that bracket, so I'm left with a perfect square trinomial that's factorable. So I'm going to take that negative 9 out, but I have to remember that while it was inside the brackets, it was being multiplied by a, so it still needs to be multiplied by a in order for me to maintain the equality within this equation. Final step is to factor that perfect square trinomial and to collect all the like terms out here. So to factor the PST, we can take the square root of t squared, which is t, the square root of 9, which is plus or minus 3. We're going to choose to make it negative because of the value of b in that PST. And then out here I have 45 and 135, which takes me to 180. And from there, I can deduce what the vertex is. So from these two pieces, I know that the vertex is 3, 180. Okay? So that means that the maximum height of the rock is 180, and this happens 3 seconds after it's thrown. This would be a 3, and this would be a 180. Like that. Part C says, how high is the rock a second after it's thrown and 5 seconds after it's thrown? Let's go back to our original equation for that. And what I can do is I can sub in that time for t. Let's put in the 1 second first. So anywhere there was a t, I'm going to sub in a value of 1. And this should give me then the height at that particular time. Let's do exponents first. So 1 squared is just 1. 30 times 1 is 30. So I have from here negative 5 plus 30 plus 135. This drops us down to 130. Add 30 takes us down to 160 meters. So this makes sense because if we look at on our sketch here 1 second after it's thrown, it's going to be more than the initial height, which was 135, but not as high as the maximum, which is 180. And 160 meets that criteria. So 160 would be, right about there. What happens, or what's the height 5 seconds after it's thrown? Well, same idea. Let's put in a 5, though, wherever there was a t. In solving, let's do exponents first. So I have negative 5 times 5 squared, which is 25. I have 30 times 5, which is 150, plus 135. This comes out to 125 plus 150 plus 135. Well, isn't this interesting? It also comes out to 160 meters. How is it possible to have two different height, or the same height at two different times? Well, let's remember how this rock is traveling. It gets thrown, it hits 160 meters on the way up, but it's also going to hit 160 meters on the way down, right there. And this happens at two different times. It happens at 1 second, and it happens at 5 seconds. And it's not surprising that those same heights occur when the x values are the same distance away from the axis of symmetry. This one's 2 seconds away from the axis of symmetry, and this one's 2 seconds away. Okay, so it's totally possible and makes sense. Our last question is, how long does it take to hit the ground? So in that case, we're looking at this piece right here? Or what's the root, right? And before we even calculate the roots, we recognize that there's going to be a positive root and there's going to be a negative root. But for the sake of answering this question, we're only interested in the positive value because of the way we've set up our diagram. So, how do we find the roots? Well, we're going to have to take our original equation and we're going to try to factor it. So, when I look at this equation, I ask myself in factoring, what is the GCF, or is there one that can be pulled out? And I'm going to set this equal to 0 intentionally for y, because I know that's a condition of x-intercepts. I look over here and I go, hey, the GCF is 5. But let's take it out being negative as well, because you can recognize now that this is actually the a value of the parabola, and it is an upside down parabola. If we take out negative 5, we're going to be left with t squared minus 6t minus, I need my calculator for that one. $27. There we go. Sorry about that. So then, can I factor what's in brackets? Well, it's not a perfect square trinomial that remains. So I'm going to think to myself, what are two numbers that multiply to give 1 times negative 27, which is negative 27, and add to give negative 6. Well, there's again not many factors of negative 27 other than 1 and 27, or 3 and 9. Now, I'm going to allow the larger one to be negative because they have to add to give a negative value overall. And there you go. There's your two factors. So because this is a 1 in front of A, I can go straight to the answer. The only way to get t squared is to have each of these be a t times t. I can put plus 3 in one of them and negative 9 in the other. So what are the roots? Well, maybe you can do it by inspection because you recognize in factored form that what you see is opposite to what you get. And the reason for that is that if I set each of these pieces equal to 0, in order to solve for t, I have to bring this term, negative 9, to the other side, which makes it positive, or here I have to bring the positive 3 over, which makes it negative. Now, as I said earlier, I've got two roots, one at negative 3, one at 9. I'm interested in the one at 9 because I'm throwing the rock in this direction. I'm not throwing the rock behind me through the cliff. So, using completing the square and using factoring can again help us solve a bunch of different problems. We'll do our final example in the next video.